Log on, tune in, find out. Another good idea from Cambridge.
Right. No? Is it on? Okay. Move back. Okay. My talk is much less technical, I think, than the previous one because I'm trying to touch on several topics, and there is quite some overlap I noticed with the previous talk. My talk actually is based on a talk I gave a few months ago in Paris for the French group, and Bertrand Joost made some PR for that French group, which I can surely recommend to have a look at its website. Let's see the most difficult part of my talk, that's to push the right buttons. Yeah? This seems to be the wrong button. Yeah?
One with the arrows?
Yes, one with the... Ah. Oh. Oh, like this. Oh, okay. So, let's see. Yeah, excellent. I really mastered it. I'm addressing both types of audiences, I think, the deterministic and the discrete event, the random simulation community. So I myself was born and raised in the OA, the stochastic simulation groups, but some of my topics will touch on the deterministic community too. Oh, now I'm going too far. That's because we are in England, you know, you keep to the left of the road, etc. My focus will be, given the context of deterministic and stochastic simulation, will be on Kriging, which is not a surprise, and also quite some attention to bootstrapping. And I don't think that in the past day we have heard much about bootstrapping, maybe virtually nothing. There are two types of bootstrapping, and that for stochastic simulation we assume, as Barry mentioned, that there are replicates at each design point, and that means that we can use the distribution-free type of bootstrapping, which means basically reshuffling your replicates. Maybe I get back to the details. Let's see, let me first do the second part. If you have deterministic simulation, it makes no sense to have replicates. And so we cannot do the distribution-free bootstrapping. We do the parametric bootstrapping because we assume it's a Gaussian process with parameters estimated from the available input-output data. So there's two quite different worlds, and if you bootstrap, you have two different types of bootstraps, and both types will be presented in my talk. Can I see who has heard of, who is more or less familiar with the basics of bootstrapping? Who's not? Who wants to confess? Okay, we go with the majority. I think I can quickly go through that. Stochastic simulation, that's the focus of the previous talk. And if you come from geostatistics, you also are familiar with measurement errors, which is a stochastic phenomenon, and that's called the nugget effect. I can quickly go through that because I think everybody is familiar with Kriging. In deterministic simulation, there is also sometimes a random effect called numerical noise, and I remember that Alex Forrester discussed that the other day. If you want to model that, then as Barry also mentioned, you add this E term, where is it, over there, what's called then the nugget effect in geostatistics. So Z is the Gaussian process, and E is basically a white noise term. Yeah, and a white noise term means that you have a constant variance over the design space. Now that's not what we want to do in random simulation, as Barry emphasized, because as we move through that design space, the variance of what we call what I call the intrinsic noise, and I think that's a term actually I borrowed from Barry. The intrinsic, it's part of it's caused by the character of random simulation. It's not the fitting error. Then things get a little bit difficult, especially if you stick with PowerPoint. And this is probably the last time I do a PowerPoint presentation. Because what happens then is that your predictor for the new point, that to the covariance matrix sigma, you add this sigma E bar, and you take replicates, so Z response actually is an average, Y bar, and that's all shown in that formula. And E bar, I repeat Barry, there is some overlap, which is not too bad, I think, is the diagonal unless you use common random numbers. And introducing this white noise term makes the Kriging interpolator not an exact interpolator. But all of that is familiar to 99% of the audience, I think. But I need some of these symbols. What's probably, I wonder whether this slide will be familiar to the audience. We use maximum likelihood estimation for the parameters of that Gaussian process, mu, sigma square, the zetas, the correlation things, and this new matrix, say the nugget effect, the intrinsic noise. And that's where I want to pay some attention to, is that traditionally what people do is they simply plug in those MLE estimators into the formulas that you find in the textbooks. And what I want to emphasize that if you plug in your estimators, all of a sudden your Kriging estimator your Kriging predictor is no longer a linear predictor, it's a nonlinear predictor. And that's why I need the double heads. Why double head? Because now I explicitly represent the fact that all my Kriging parameters or my Gaussian process parameters are actually estimates. And when you look at the last term in this nasty expression, you see that's a highly nonlinear result that you're getting. You are multiplying random factors and matrices, you're taking inverses. So that certainly is not linear. And that implies, it's something that I think may be mentioned in passing in the textbooks. That implies that the standard prediction error, the variance of the Kriging predictor that you find in the standard literature is actually wrong. And I tried to formulate that the expected value of that standard predictor variance is not the true variance of this nonlinear estimator. Yeah? And I'll come back to the solutions that I have for this problem in the next slide, I think. In random simulation, as Barry again mentioned, is that from the replicates we can estimate the elements on the diagonal of the covariance matrix of the noise, the intrinsic noise. If you have common random numbers, I know Barry is not very much in favor of common random numbers. We had a discussion several years ago at the Winter Sim after his talk. In practice, most people use common random numbers. Practitioners use common random numbers unless you tell them not to do so. And the default of much software is common random numbers. So if you use common random numbers, your matrix of the white noise, or not the white noise, of E, the nugget effect, must be estimated. And I think, I didn't study that in detail, that the number of replicates then needs to be bigger than the number of points. And that goes back to a result in Dijkstra in the 1950s, I think, in a different context. But this estimating the correlations created by the common random numbers, that has nothing to do with Kriging in itself. That's a nicely isolated problem. That's an old problem. What is interesting, especially for those people interested in efficient global optimization and expected improvement, and that's one of the next slides, is that the traditional estimator, which I denoted as S squared of sigma y, this is the first one, and the true or the alternative estimator, which I called S square, do not reach their maximum at the same point. I didn't write that down, but they do reach their minimum at the same point, namely the minimum is 0. At all points, if you do a prediction at the all points, the variance is 0. Except if in a random simulation context, of course, it's not 0. Okay. So how do I propose to estimate the variance of the Kriging estimator that of course uses MLE estimates or estimates of the true parameters? I propose parametric bootstrapping, assuming that we are using deterministic simulation. Yeah? And I played a little bit in the past few years with this parametric bootstrap. So how does that work quickly? You have your original data set, input-output data set x, y, and from that original data set you estimate your parameters mu, sigma, theta. Okay? That's standard. Now I'm going to use those estimated parameters and the assumed Gaussian process to sample from that Gaussian distribution, multivariate Gaussian distribution. So I sample the n data points, and n is the number of what we call old observations, and I at the same time, that's a technicality, maybe that becomes clear in the next lines, I sample the true point, the true observation at the new point, which is called x n plus 1. So from 1 to n is the old data, n plus 1 is the single new data point. And I sample them from a multivariate normal distribution with the parameters that are estimated in step 1. I hope that's clear. What do I do next? From that bootstrap sample, and the bootstrap sample is denoted by the superscript star, from the bootstrapped old data, I again use MLE to estimate the parameters. And I denote that by mu star, etc. So what I get in step 3 looks like what I get in 1, but it's certainly different numerically. Yeah? This is the crucial step. And then remember that sorry, I'm getting ahead of myself. From the results in step 3, I'm now going to predict the output at the new step using the parameters obtained in step 3, if you are still with me. And then in step 5, I combine the results of step 4 and 2. I say in step 4, I have a predictor based on the bootstrap, and in step 2, I had not a predictor, I had the true value, which I denoted in green in step 2, and I compare the two, and I take the square difference. And then all I have to do in bootstrapping is I repeat this 100 times or so, it's the magic B, and I take the average value that I got in step 5. Yeah? So that, I think, is a rather simple estimator, but on the other hand, I remember that it took me quite a bit of time to explain that to people who are familiar with Kriging. So I don't know how you feel. So if you feel, gee, what's this guy talking about? You are in good company. Like I had a visitor, Don Jones, who was the inventor he was a main character in the play around the expected improvement stuff, and it took him a while to understand what was going on. And then he was convinced that this was the way to go. Let's see an application of this approach. We applied this idea to quite a realistic circuit simulator, a deterministic circuit simulator that was used in the standard article by Sachs and Mitchell and Wynne and whoever. It's the classic article, 89. I use this bootstrap variance as an alternative for the standard predictor variance in the context of ego slash expected improvement. Ego expected improvement has been mentioned by several people in yesterday and the day before. So I realize now that I can go quickly through what is ego. It's trying to balance the global exploration versus the local search. I think that was not mentioned explicitly by the previous speaker in the previous days, assuming that people knew this stuff probably. So it assumes the original ego assumes deterministic simulation and a single output that you want to minimize. And this is the algorithm, and I will go I will just repeat what has been said in the past days, right? I go back one step. So this has been explained by the speakers in the past days. That's how ego works. And you see the crucial role, there is a role for the estimated variance of the predictor, and that's this, it's shown in green, and it's also still here in green, in step 2. And so I claimed 2 slides ago that actually is a bias estimator. And my alternative is the bootstrap estimator. So what we did is we just took this algorithm but replaced that green expression by the bootstrap estimator of the previous slide. That's all. And we didn't manage to arrive analytical steady state or convergence properties, but we did apply it to 4 test functions, and one was mentioned yesterday, the Brannin function. That's in 2 dimensions. We also applied it to a test function in 1 dimension that Alex Forrester proposed. We applied it to the so-called Hartman function in 3 and in 6 dimensions. And it turned out that the bootstrap, if you use the bootstrap estimator of the variance, you do better in 3 of the 4 test functions, and in the remaining single test function was a tie. Yeah. Now, before you rush and throw away your ego stuff, the good news is that if you take a big pilot sample, etc., it doesn't seem to matter too much. So our method is quicker. I don't think it's dramatically bigger, but you would have to read. This has been published in the Journal on Global Optimization, I think this year. A different approach to optimization using Kriging has been developed a few years ago by some of my co-authors, one from Belgium and one a former PhD student of mine. And it was motivated by an example that Barry mentioned this morning, the call center. And actually we took the call center simulation from a textbook explaining the power of ARENA. It has a very detailed call center simulation, so detailed and so complicated that in 1 edition it was thrown out of that chapter, and then in the next edition it came back again, and I didn't check what the current situation is, because this software keeps being updated, new editions, etc. And the idea of the challenge of this problem is you have a call center, don't have to explain what that is. You want to minimize the cost. Of course, you can minimize the cost by closing down the call center, basically, right? But then your service is so-so. And sometimes you have the impression that's the way people go, if you call a call center. But we want a service that's like 95%, meaning that in 95% of your calls you get within so many minutes an answer. So that's the motivation for constrained optimization. So we want to, the constraint is that the service should not go to 0 in this example. In more general terms, we have multiple outputs, and I think in simulations that's very, very realistic. You always have multiple outputs. Then the way we went, being trained in operations research, we took a mathematical programming paradigm, I would say. We picked one of these types of outputs as the goal variable that we want to minimize. Being an economist, you would minimize the cost probably, yeah? And then you have a number of constraints, like the service is one constraint, but depending on the application, you might have more constraints, etc. So you have multiple outputs, they are denoted Y0 through YR in these symbols. There are more constraints actually. There are also constraints on the input side. So we have a number of inputs, d dimensions, that's the popular symbol, we have d dimensions, and we have constraints on the inputs, and these are not necessarily linear constraints. This actually is related to the talks that Angela gave yesterday, I think. And there's a final constraint that has not yet been mentioned, I may not paid much attention to, is that our inputs must be integers. Because we are talking about number of people that we hire and number of telephone trunk lines that we buy or hire. They're all integers, which makes the problem a bit more difficult. So that's the general problem class. And the solution that we use combines sequential design of experiments, like EGO does, but then using a very different approach. It uses Kriging and bootstrapping. Actually, here we use the bootstrapping to validate the fitted Kriging models, and that's a pretty long story that I'm going to skip. I'm looking at the watch. You should be waving your hand, and then I promise to wave back very friendly, you know. And so we have multiple outputs. We fit a Kriging model for each output. So y0, y1 through yr. We have r Kriging models, and to such Kriging models we apply nonlinear integer programming, because the constraints are nonlinear, and integer because the axis must be integer. And so for the what's interesting, I think, is that for continuous inputs, like Barry and Bruce were discussing, we would have the gradients for free once we fit the Kriging model. So that would be useful information. That's a different type of gradient information than what Barry was talking about. I want to talk to him about that later on. And in deterministic art, if the situation would be deterministic, it would be, I think, similar problems. Also in deterministic simulation, you have multiple outputs. You want to satisfy certain inputs, or outputs, sorry, and you also have constraints on your input, etc. Then I think it might be a good idea to skip this slide, yeah. So I'm not simply waving back now. This gives the details of what we have been doing, and this has been published in 1 year ago, and you can download the paper on my website. Okay. Final topic, quite different topic. We want to fit Kriging models, but I realized a while ago that sometimes you know that your input-output function is monotonic. And an example is the queuing examples, where we know that as traffic gets heavier, we have to wait longer. And so the Kriging model should satisfy that requirement. In a regression analysis, there's also some people who are working on regression analysis under that constraint that we know that it should be monotonically increasing. And the technical term escapes me for isotonic, that's what I was looking for. And also rank regression does the same thing. But I haven't seen a Kriging that realize that. And I have a very simple solution, maybe so simple that something must be wrong. But let's look at it. So we assume random simulation. The challenge is to do this for deterministic simulation without replicates, so that instead of distribution-free bootstrapping in deterministic simulation, you would use parametric bootstrapping. The result of the bootstrap approach that we use, and I will show that very quickly in the next slide, is that we get better coverage. So our confidence intervals for the true mean are better without getting wider, because it would of course be like cheating if you take a confidence interval from 0 to infinity. You would have perfect coverage, but that's not the idea. I think that what I would like to do in the future is replace this We use classic Kriging because at the time we did this research, we had no access. Maybe were even not aware of the work that Barry and Bruce were doing in stochastic Kriging. And so we were using classic Kriging, fitting the Kriging model to the average over the replicates. I think what also would be interesting is to extend our approach from monotonicity preserving Kriging to other types of characteristics that you know about the system, like convexity or non-negativity. For example, if your output is a waiting time, you know that it never can be negative. Now the Kriging model might predict negative responses, so that would be silly. And as I mentioned this before, I think that deterministic simulation would replace the bootstrapping. This is basically, people know about bootstrapping, so it's a resampling. We have, in step 2, we have averages, so we can resample, we get new averages. In step 3, we compute we fit the Kriging model to the bootstrap outputs. I can quickly go through it, because the essential step is step 4, shown in red. We accept only Kriging models that are monotonically, we accept only those bootstrap Kriging models that are monotonically increasing, meaning that they have positive gradients, and that's easy to check. And it's bootstrapping, so repeat, and the point estimator for the predictor is then the median of the B bootstrap Kriging predictors that you have. Actually, I said the B dash Kriging predictors because you accept only those monotonically increasing B Kriging predictors. And what I also like about it is that the confidence interval is very simple. You don't use normality. You take the 5%, the 95% quantile of your B dash bootstrap predictors. The confidence interval is asymmetric, if you think about it. And you never can get a confidence interval where the lower point, for example, for the waiting time would be negative. So that's it. Right on time.
I believe it's time for lunch, but if anyone's interested, we could have a quick question for either group of speakers.
So what was your acceptance and rejection rate when you're doing this bootstrapping?
Oh, that's a good question. Do I know that? It must have been pretty high, because otherwise that would be a worry. It was not 100%. But I don't remember the details. My guess would be something like 90% or so. Yeah, but that's a guess. Yeah. Because if the acceptance rate would be very low, you would do a lot of bootstrapping, and that would have been a worry for us.
It would depend on the function.
Yeah, this was a queuing model. Yeah, yeah. So it's only one case. Actually, I would like to do another case study with the SS inventory model. That's high on my agenda. Okay?
I was wondering whether your monotonic method might already solve your convexity problem for you if you applied just simply to the gradient.
Yeah, yeah. Yeah, I didn't try, but I think that if you believe that this is a good way for the monotonicity, convexity is simple, and also non-negativity is simple. And these are things that in practice I think are important. Yeah. Could I ask a question? Or maybe because I have a question for Barry. You have the gradient estimator from through IPA or score function. Once you fit the Kriging model that incorporates those gradient information, the Kriging model also gives you a gradient at the observed values or all the other values. Did you check the two gradients?
Yes, that's additional research that we're doing. And at least in what we've done so far, you're much better predicting the gradient surface by fitting the gradient estimators than you are by taking the gradient of the response function.
Okay.
Okay, go ahead, please.
Sorry, just one thought about accepting the estimators that satisfy the property that you're looking for. in a sense, what you're doing is you're conditioning on having the property that you're looking for from the class of Kriging estimators that might be produced. Is that the same thing as, first of all, imposing that structural requirement and looking at the distribution that would result? So,
The distribution of what? Of Kriging predictors? Kriging models?
I'm sorry, I don't really know exactly how to phrase this question in a clean way, but essentially there's a structural property that you know you want to impose. And so then you say, well, let's do some Kriging. And what your estimator really comes down to is ignore that structural property, I think. But then only accept those that satisfy that property. So it's sort of the conditional distribution.
So we don't impose the condition, we just take an unrestricted sample, and that was the other question. Then we only accept a portion, and of course a very practical question, is that portion acceptable? In our experience the answer was yes. And by the way, this whole problem disappears if you have enough observations. And so I would recommend that you start with the classic Kriging, and then see if the classic Kriging, without doing any special things, is acceptable. If you have enough observation, but we found that in queuing, if you have 5 points and we replicate them 5 times, we got some wiggling results. Okay?
Okay.
Two announcements. Tomorrow, Thursday.